So circularly, just I'm trying to bring out the circularly polarization into the hybrid dielectric resonator antennas. Up to now, we have seen only how to design hybrid antennas, hybrid dielectric resonator antennas. Now you are incorporating circular polarization into the hybrid dielectric resonator antennas. Next. So the what I've done is I've taken a simple electromagnetic coupled antenna. Electromagnetic coupled antenna is different from the aperture coupled antenna. So here what happens is two substrates will be there, and feed line is in between the two substrates, right? On the top of the substrate, you're going to have a patch, any shape of the patch. So what I've done is, in order to get the circular polarization, I've taken a slot that is asymmetric hexagonal slot across 45 degrees of the patch. So and with that particular configuration, I'm achieving without dielectric, I'm achieving circular polarization. Well and good. But I want to utilize the advantage of the dielectric. What is the advantage of the dielectric? It can increase the bandwidth because it is going to confine the field of radiation into that shape of that, and it is going to stay more amount of time. It might give more bandwidth as it is a property of the dielectric, right? So while analyzing this particular antenna, so what I've done is, so I've done split ring is placed at 45 degrees, 0 degrees, 30 degrees, 60 degrees, and 45 degrees. 45 degrees, I'm generating two modes, two orthogonal modes. This is fine. It's only patch. Next, dielectric is not loaded on this. Dielectric is not loaded. You can see 0 degrees, 45 degrees, 90 degrees, 135 degrees. The field is rotating, right? Circular polarization is achieved. But how to bring the wider bandwidth when compared to this microstrip? So you know that microstrip patch antennas basically 10%, 5% of bandwidth. Base. I mean, in the textbooks you can see that, but you can increase the bandwidth by using dielectric resonator antennas, right? So I'm trying to exploit that. So what I've done is I've placed a dielectric block at the radiating edge of that particular hexagon, where exactly the more radiation is concentrated. Where exactly it is concentrated? It is concentrated at the edge of the hexagonal ring, right? So there I have placed a dielectric block. Next picture. Next. So now after placing dielectric block, the bandwidth has been increased. You see here, it is radiating at 2.6 gigahertz North American LTE band, long-term evaluation band. And the black one is split ring loaded patch. The red one is proposed hybrid DRA, where after placing the dielectric block, you can observe that particular radiation also in the field analysis picture in the next slide, right? See, after placing the dielectric block at the edge of the radiating edge of that particular hexagon, see the bandwidth is increased, and also it is giving wider beam width. Okay, in YZ plane, the patch configuration is also giving, and also after placing the dielectric block, it is giving 200 degrees of wider beam width when compared to the patch, right? So that is, you can convert normal patch antennas into hybrid, and you can check whether it is enhancing the features of the antenna or not. Right? Next. So this is XZ plane and YZ plane patterns, and this work is published in IEEE conference is in happened in Montreal in Canada. Next, and this is the collection of my postdoc work in Canada, as that already explained. The first one is a different one. It's actually it is a meander line edge conical meander line antenna. So where you can use it for circular polarization, circularly polarized applications. You can see the bandwidth and axial ratio and the return loss and everything, and the composition of the antenna. You can see the current distribution for 0 degrees, 30 degrees, 90 degrees, and 135, all the angles, right? So next. So literature review for the hybrid dielectric antennas, what I've done is I asked my scholar, actually this from here onwards, my scholar's work is going to come. So I asked my scholar, first review all the dielectric antennas and review papers, not if you take a review paper, what happens is all the different techniques will be studied in that particular paper, so that it will bring almost more than 200 150 papers, so that one single paper is going to give you a clear picture. So I've asked him to do a review for review papers review, right? So he has formed a table. In 1994 there is a review paper on different DRA shapes, and 2005 application oriented and advancements challenges, and until 2020 there is different types of CP antennas, CP methods. He has studied all these review papers. He has given a table. So if you do a review paper, so you could understand where exactly the need is there, and where exactly the narrow areas you can find out narrow areas of that particular uh, work, and you can work on those narrow areas, so that your work is going to be recognized and you can bring out some novelty, right? Next. So this is a comparison of wideband antennas and multifunctional antennas, different tables. So very less hybrid antennas are proposed until 2020. And then next. So this is one of the antenna. So here I have it with me, and this is see, you can see that is what I'm talking about, the bonding, right? These are four layers are there. Four layers are attached to in order to bring out this total height, because you won't get this is very costly material, because this is epsilon r 10.2 roses 6010, and you will get only 10.16, I mean 2.54 mm, I means 1 inch, 2.54 mm only you'll get the height. So in order to get the 10 mm, what I've done is I've stacked four elements. So in order to stack it, I have used a glue. That glue is also you should consider in the simulation, otherwise you won't get better result, right? So this is what I've done is, you it looks like symmetrical antenna, it's symmetry in nature, but it is not symmetric, because the feed is asymmetric. Feed is given at the edge, and the patch is a circular ring, and DRA is in between the circular ring, and the common feed has been used. That is an all common feed has been used for both the patch and DRA, right? So all this particular work, I mean, my scholars work is designed at 5 gigahertz only, right? So 5 gigahertz WLAN applications. So we can variate the DRA height, and you can variate the probe height, and that study has been done. And this asymmetry is giving us circular polarization, right? Next. So this is the composition of the antenna. See, initially there is no radiation at all. For the DRA, it is around very less return loss is there. It is around 4 gigahertz. And after bringing getting together ring and DRA combined together, you're getting 5 gigahertz, right? So you have to estimate these things through the equations that I've given earlier. So by taking the frequency and epsilon r values, you have to appropriate that particular fundamental resonance, and then you have to do the simulation, right? Next. So this, see, the CP radiation, you can see then HEM, this is actually a hybrid electromagnetic mode is generating. So HEM delta 11 mode is in X direction is YZ plane, and HEM 1 delta 1 mode is in Y direction is the opposite side. That means that the two orthogonal modes are generated, and they're producing CP radiation, right? Next. So the similar parametric study that I've told you about, different feed lengths and also different diameter of that cylindrical DRA. Next. And it is measured and tested. Go on. Yeah. So it's measured and tested. This work is published in MDPA journal, and that's corresponding plots and comparisons and everything. Anil, you can speed up. Yeah, right. So the performance comparison next. Yeah. So this is another antenna. Actually two antennas I'll explain together. These are two antennas we have used. This is how it has become hybrid is, you can see a meta surface below the DRA. See, you can see the meta surface below the DRA. The DRA is placed on the meta surface so that the feed is taken care of. That feed is not attached to the meta surface. Okay, meta surface is excited through the DRA placement. Okay, so the feed is directly attached to the DRA, then the radiation will be attached to the meta surface. So how this particular meta surface acts is, meta surface, here the feed is penetrated probe feed. I mean, it is a perturbed probe feeding, you can call. I mean, some portion of the DRA will be etched, I mean, grooved, and the probe will be penetrated into that. So because of that, the attachment of that particular probe is more when compared to the direct attachment. So the penetration is going to give you more attachment to the DRA, right? So here, what I've taken is, I've taken Minkowski metasurface, a single unit metasurface. It's actually, basically, it is a not square, it is a rectangle. So both the sides are not equal, but the dimensions are taken as x is divided into 3 and y is divided into 3, and x by 3 and y by 3 is, that portion is going to be etched out. So that is how the unit cell has been prepared, right? So first you have to see for this particular substrate and for this particular unit cell, whether it is giving reflection phase characteristics or not, right? So yesterday, very clearly, Samsiro Garu explained about metamaterial concept, right? I'm not going in detail with that, right? So the reflection phase characteristics should show 0 degrees phase difference at that particular resonance, right? The phase difference is exactly around 5 gigahertz. Okay, zero phase reflection phase is at around 5 gigahertz. That you have to check before considering that particular unit cell, right? Then uh, next. So then what I've done is, so uh, I placed a DRA and I've tested for surface current. Surface current is only taken for meta surface because DRA is a non-metallic object. So you have to show the surface current. Here, what I've magnitude of surface current I've taken, theta 0, 45, 90, and 135. So you can see the field rotation. So that the DRA is obviously achieves CP radiation, but this CP radiation maximizes by including this particular metasurface, and metasurface is also influence the frequency to come shift towards the lower band. That is what the yesterday the Samsaroga explained at lambda infinity. If you place lambda infinity, frequency is going to be very less. When lambda is maximum, frequency is going to be very less. That means that the higher frequency resonance will be shifted to the lower resonance, right? So that is the advantage of taking the meta surface. Up to now, I've taken only patches in order to prepare the hybrid antennas. Now I've taken material concept also taken to bring the constructional change in order to form a hybrid nature of that particular antenna, hybrid kind of dielectric resonator antenna, right? Next. So there are different configurations, 4 different configurations, composition of that particular antenna I've taken. You can see the simple DRA figure A 4.4A is showing that it's resonating at around 6.25. But after placing meta surface and 5.5 by 5, 7 by 5 onto that, it is bringing down. It is bring down to 5 gigahertz. That is what yesterday's class they has explained, that mu negative, epsilon negative, mu 0, epsilon 0, velocity will be infinity. If the velocity is infinity and then lambda is infinity, then frequency is shifted towards lower resonance, right? So that is the concept. Even the gain is also improved when compared to the 4 configurations. That is clearly it is showing here, right? Next. Next, this is the return loss variations for different parametric variation, and then this is antenna is tested in Bitspilani laboratory. It's a Lambda laboratory. It's called Lambda laboratory. and this is measurement. Next is radiation pattern and acceleration measurement and gain comparison. And this is somewhat different. It looks same. The dimension, outer dimension of the antenna is same, but the meta surface is different, and also the DRA is also different. There is a halo in this DRA. Actually, in Aldo Petosa, if you study, or Lucan de Jong, if you study, if you take a halo region inside the DRA, the bandwidth is going to be is increased, because the energy is going to be, amount of energy is going to be fluctuated inside, wobbling inside the halo region is going to be more. So because of that halo region, the bandwidth is going to be increased. That is one of the bandwidth enhancement technique that has been given. That technique I picked up and I've added. That is the difference in these two antennas is, one is unit cell is different, another one is DRS size is more, base size is less here, more is here, and there is a halo region inside. Here there is no halo region. This is solid antenna. So there are this, with this difference he has done. See, you can see diameter D1 DI is halo region, diameter D0 is the outer diameter, right? That is the constructional change I've brought. And also the unit cell is modified Jerusalem cross unit cell. This is a regular unit cells I've used. Next, so the phase, reflection phase characteristics in order to understand the metamaterial concept. And then next, so the circular polarization concept, and then the antenna uh, modeling and testing and that particular frequencies. And next, so comparison of both the designs and comparison with the earlier work. And these two antennas are both are operating at 5 GHz, but the first design, Minkowski design, is going to produce around 7 dBi gain, and the second design is going to give you around 6.98 dBi, and with the wider bandwidth of around more than 500 megahertz. This is another one of my postdocs work, and also my scholar is parallelly worked on this particular work. So this is a very small antenna, small DRA. I wanted to bring it in the end, because see, the asymmetry is brought here. There is a small patch, circular, semicircular patch, and a small semi-cylindrical DRA. Both are combined together with one probe feed. Both are combined together, one probe field, and this brings the CP radiation, right? So this is a very beautiful work, another beautiful work. This is published in Willy journal, and earlier both the works are published in MDPI journals. You can see the patch, semicircular patch is going to radiate at higher frequency, and the cylindrical DRA is going to radiate at lower frequency. Combined together is going to give you the wider bandwidth across the frequency, right? Across the whole frequency, lower and higher, both together is going to combine together, and you're going to get two CP modes, because both are asymmetric. Both are asymmetric in nature, and fed by single profit. That is the novelty, right? Next, this is field and surface current distribution. This is, you can see here in the antenna, the semicircular patch is combinedly fed by a probe fed to the semi-cylindrical DRA also, right? It's tested in Canada in my laboratory, there in the college university laboratory in Canada. And then next, so this is a two CP modes with good isolation. Isolation is should be, if it is multiband antenna, isolation should be more zero. It should be close to zero. It should be above -5 dB, right? Not below, right? So both are giving axial ratio, and the gain is also isolated perfectly. So these are the results that I have achieved in the laboratory and simulation, as well as measured. Right. Next. These are the patterns. XZ plane and YZ plane both are similar. Next. So it's compared with the proposed work. This is also patent is granted, and also it is published in SCA journal.